Hi there, this video has to do with the internal organization of our planet. Many of the things that we perceive or can see here in the surface, this is on the Earth's crust, are a direct or indirect manifestation of what is underneath us, below our feet. Today, we will review the internal organization of our planet and the criteria we use to classify and distinguish the different layers that compose it. Enjoy, and don't forget to like, share, and subscribe. Our planet is a dynamic entity with multiple interactive parts. Modern geology approaches the study of the Earth as a whole system, that is, a group of interacting or interdependent parts that form a complex whole. The internal dynamics of our planet reflect this interdependency, that in turn is largely dictated by its component materials. Many of the geological processes that we see in the surface of our planet can be better understood if we know the composition and properties of all the layers that compose its internal structure. The Earth has its own ways to arrange the materials that compose its interior. Like in many instances in nature, the internal organization of our planet is governed by the laws of nature like gravity and electromagnetism. Also, because different materials have different properties such as density, they behave differently and exhibit different properties. Today, we see the internal structure of the Earth as an orderly arrangement of different elements bonded to form different compounds and segregated by density, resulting in a layered structure, where each layer is not isolated, but rather related in some ways to the others, or even with us here in the surface. We can study the internal characteristics of the Earth using two types of observations. We can employ direct observations. These are observations where we interact with the object or phenomenon we are studying. In this way, we can see, touch, or interact directly with whatever it is that we are observing or studying. However, when the object or process under study is too far or too deep, like the ocean trenches or the center of the Earth, what can we do? Well, in these instances, we can employ indirect observations. Indirect observations are those where we don't directly interact with what we are studying. For example, a far, far away galaxy or the internal layering of our planet. When we study the Earth's internal structure, we can employ these two methods in different ways. For example, we can see volcanic eruptions or even lava flows in spreading centers in the deep sea, like this one right here. These direct observation methods occur here on the Earth's surface. In these cases, we see the lava pouring out and we can even sample it. However, to study and understand what happens below our feet, within and below the Earth's crust, geoscientists employ for the most part seismic waves from earthquakes. Seismic waves from earthquakes behave differently depending on the characteristics of the medium they are moving through. They provide information on the characteristics of the Earth's interior such as composition, physical properties, and even boundaries, among others. The result of these two different approaches using direct observations or indirect observations like seismic waves to study the internal structure of the Earth has demonstrated that our Earth is divided into layers distinguishable by their physical properties and also layering that is distinguishable by their chemical composition. Let's talk about each one of these types of layering. The differentiation of the materials that compose our planet began a long time ago, early in Earth's history. The result of that process led to the formation of three major layers defined by their chemical composition: the crust, mantle, and core. Although we cannot see the process of chemical differentiation as it involves several layers below our feet, this internal process continues today, and it contributes to the internal arrangement of our planet in different layers. At this stage, we also must say that it has been operational since very early in the history of our planet, perhaps beyond 4,000 billion years ago. That's a long time ago. As material accumulated to form the Earth, the high-velocity impact of the nebular debris and the decay of radioactive elements caused the temperature of our planet to steadily increase. During these times of intense heating, iron and nickel began to melt, producing denser blobs of liquid metal that sank toward the center of our planet. This resulted in the Earth's dense iron-rich core. Continuous chemical differentiation during this early stage of our planet resulted in the three basic subdivisions of Earth's interior: the iron-rich core, the thin primitive crust, and the Earth's largest layer, called the mantle, which is located between the core and the crust. we must start by the definition of a word layer. In this context, we say that each layer is a sheet-like mass of rock of one kind and properties lying between the layers of other kinds. It implies an orderly arrangement by properties in a way we can anticipate what the next layer could be, if that makes some sense. Well, the Earth is organized in layers too, based on gravitational segregation due to the differences in density and the differences in elemental and mineral composition. Let's explain this concept using this diagram. The core, that is composed of iron and nickel. The inner core at the very center of the Earth is the densest and is surrounded by the outer core, that is liquid. The core is then surrounded by the mantle, that is overall high-density rock, with the lower and upper mantle being solid rocks. Following is the outermost layer beneath our feet, the crust, the relatively thin, rocky outer skin of the Earth, sort of the skin of an apple, the outer skin cover, as you can see here. This is overall less dense and is further subdivided into oceanic and continental crust, mainly because of its mineral composition. Of these two, the continental crust is the lightest, composed mainly of felsic minerals, in contrast to the oceanic crust, dominated by the denser mafic minerals. And if we keep going up above us, we can start by saying that the crust is denser than the water of the oceans that overlay it, and then it is overlaid by the mixture of gases that make up the atmosphere that is even less dense, and almost out is the empty outer space. Thus, the densest elements are at the center of the Earth, like iron and nickel, and the lightest elements are in the outer side, like oxygen and nitrogen, that we breathe and that compose the majority of our atmosphere. The early atmosphere resulted also from the early period of chemical differentiation, as large amounts of gaseous materials escape from the Earth's interiors towards the outer parts. Because of this layering, our planet exhibits different physical properties, including properties such as ductility and fragility, among others.
A remarkable thing to note about the internal dynamics of our planet is that although these layers do have a different elemental and mineral composition, they are not isolated or static or have shared boundaries between them. To the contrary, they interact with each other and there is a continuous energy exchange among them, allowing them to be a complex dynamic system that follows the rules of nature and result in different physical characteristics.
And these are the very physical properties that also serve as the basis to subdivide the Earth's interior. In previous videos, we have remarked that the physical properties of the materials of the Earth, like the minerals and the rocks, depend largely of their composition and crystallographic arrangements. Well, at a larger scale, these approaches can be also applied to our planet's internal structure. However, the physical properties used to define the internal zones of the Earth include whether the layer is solid or liquid, and how weak or strong it is. That is a function of both their composition and the temperature and pressure of their environment. The characteristics of our planet's interior is determined by analyzing seismic waves from earthquakes. As these waves of energy penetrate the planet, they change speed and are bent and reflected as they move through zones that have different properties. From their study, 4 major zones can be differentiated: the lithosphere, asthenosphere, the outer core, and the inner core. The lithosphere, averaging about 100 kilometers in thickness, however, is more than 250 kilometers thick below the oldest portions of the continents. The lithosphere is made of the crust and the upper mantle, broken into the plates and plate tectonics, that is solid and rigid. Nonetheless, rocks here are progressively hotter and weaker, therefore more easily deformed with increasing depth. The asthenosphere, from the base of the lithosphere to a depth of about 410 kilometers. It is weaker compared to the stiff lithospheres. That means that the asthenosphere is solid but mobile. From about 410 kilometers to about 660 kilometers in depth is the part of the upper mantle called the transition zone. The top of the transition zone is identified by a sudden increase in density from about 3.5 to 3.7 grams per cubic centimeter. This is because with an increased pressure, new denser minerals form. The lower mantle, from a depth of 660 kilometers to the top of the core at a depth of 2,900 kilometers, is stronger than the asthenosphere. That means the lower mantle is solid and overlies the molten outer core, that is liquid, a layer of 2,270 kilometers thick. It is the movement of the metallic iron within the zone that generates the Earth's magnetic field. This liquid is made of the same iron-nickel alloy as the inner core, but the extremely high pressure of the Earth's center compacts the inner core into a solid form. A remarkable things happen here. The inner core, that is a sphere that has a radius of 1,216 kilometers, despite its higher temperature, the iron in the inner core is solid due to the immense pressures that exist in the center of the planet. This video deals primarily with the composition and physical properties of the layered internal structure of the Earth. The characteristics of each layer are largely dependent on the elemental mineral composition of them, which in the end is reflected in their density. To study them, we can employ different methods that may involve direct and indirect observations. Even though the Earth is so thick compared to the scale of a normal person, and the distances of each layers are quite large, what happens internally affects us here on the surface. This is because the parts of the Earth systems are linked so that a change or increased activity in one part can produce change in one or any of the other parts. For instance, when a volcano erupts, pyroclastic material, ash for example, goes up in the atmosphere and can diminish visibility in the sky, making difficult or even risky to fly over certain areas, leading to the closing of air traffic and the disruption of the global supply chains. Another example is that lava from the Earth's interiors may flow out at the surface and impact entire neighborhoods in cities or rural areas, including road blockages and forest fires that impact human and wildlife. Thank you for watching up to this point. I hope that you learned and increased your amazement and admiration towards our planet. Please let me know in the comment box which method to study the Earth beneath us you've heard of. Perhaps seismic, ground-penetrating radar, sampling of lavas, seismic waves produced by earthquakes, etc. I like, for example, the study of seismic waves from earthquakes because we can feel and sometimes we can see the effects on the surface even when they occur very deep inside the Earth's crust. Let me know below in the comment box and I will do my best to answer all your comments. Don't forget to like, share and subscribe, and I will see you in our next video. Ciao!